The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu and I will respond as soon as I can. All right, so today we're going to go on to section 11.4, but before we do, we have a problem that came in by request. So let's take a look at that. And this is number 16 in section 11.3. It says the charge remaining in a battery decreases as the battery discharges. The charge C in, I believe that's coulombs, I'm not sure, after T days is given by the formula C equals 3 times 10 to the negative 4th power times 0.7 to the T power. Find the charge after 6 days. All right, so C is the charge, T is the number of days. So if we're to find the charge after 6 days, that means we want to put 6 in the place of T. So we're going to take this formula and we're going to put 6 in place of the T. Going to our calculator, parentheses 3 times 10 to the negative 4th power, close parentheses, parentheses 0.7 to the 6th power, close parentheses. And I get this, I get 3.52947, and then it says E negative 5. And what that E is basically saying it's in scientific notation. So that would be 3.52947 times 10 to the negative 5 power. Now, it's said to round your answer to 9 decimal places. When I did it on my calculator, it didn't take it out to 9 places. So anyway, and I see an answer that's been accepted there, and it's not rounding to 9 places. But anyway, I think that should work just fine. We okay with that? Any questions there? All right. That was the only question that came in. So now we're going to go on to section 11.4. Okay. So an exponential equation or an exponential function has the variable and the exponent. But what if we needed to solve for that variable in the exponent? Let me just give you a scenario. Let's say 2 cubed. Well, 2 cubed is equal to 8. And 2 to the 4th power is equal to 16. So somewhere in between there would be 2 to the x, and let's say 11, okay? So if 2 cubed is 8, and 2 to the 4th power is 16, and 2 to the x is 11, since 11 is between 8 and 16, x must be between 3 and 4. And we could sit down in our calculator and go 2 to the 3.1, 2 to the 3.2, 2 to the, and you know, and through trial and error, we could get an answer to some reasonable number of decimal places. But that could take an awfully long time. So what we want to look at is how can we take an equation where the unknown variable is in the exponent and solve that equation for that unknown variable. And what we're going to be using is something called logarithms. Basically, if we take 2 to the x power equals 11, we can rewrite that as an equivalent statement. Log base 2 of 11 equals x. Now, log base 2 of 11. My guess is none of us have any idea what that is at this point, but I now have an equation where x is isolated. So if I can figure out what that is, what log base 2 of 11 is, I can solve for x, okay? Later on, we're going to come back and we're going to finish this problem, but we don't have the tools and won't have them for a day or so yet to solve it. But I just wanted to give you a scenario of, okay, here's a case where we want to know what the exponent is, and it's a variable. All right, now let's take a look at this situation. And what we've got from that is this statement. If we have x equals b to the y power, that is equivalent to, and this is like a two-way arrow, y equals log base b of x. Okay. Now, what I want to do is first I want to go through and look at the names of things. X equals b to the y power. The y is the exponent on the b, and the b is the base. If we look at the logarithmic equation, the way we say that is y equals log base b of x. Okay, so my point is this: in both the exponential form and the logarithmic form, the base is b. Okay, now going back to the exponential form, here we have y as the exponent connected to the b. In the logarithmic form, we have x. It is connected to the b, but it's not b to the x power. It's log base b of x. But what I want to talk about now, this is a way that I remember how to go back and forth between these two forms. Let's talk briefly about an inning of baseball, okay? Even if you're not a fan of baseball, my guess is you know a little bit about it. In an inning of baseball, there are two teams playing against each other. One team we say is up to bat, and the other team is out in the field. Now, in the infield, there are 4 bases that players run around, okay? Now, when the team that's up to bat gets 3 outs, what happens? The players change places. The team up to bat goes out in the field, the team out in the field comes up to bat, okay? When the team that's out in the field comes up to bat, do they go around the infield and pick up the bases and bring them into the dugout? We talk about a stolen base. Is that what that's referring to? Do they pick up those bases and take them into the dugout? No, the bases stay the same, but the players change places. Now, what does that have to do with what we're doing here today? This base is B. This base is B. The base stays the same, but the players, the X and the Y, change places. Here, the Y is connected to the B. Here, the X is connected to the B. But again, I want to point out this is B to the Y power. This is not B to the X power, but they are connected. So how does that work? Let's say I've got 2 cubed equals 8. All right. So 2 is the base. If I were to take this exponential equation and write it in logarithmic form, it would be log base 2. But log base 2 of what? Of 8 equals 3. So here the 3 is connected with the 2. Here the 8 is connected to the 2. The base, the 2, stays the same. The players change places. Now, that's not very mathematical, but that's just a description that I use to remember that. And there are many other descriptions out there if you don't like this one. Okay, now, any questions on that before we move on? All right, so we're going to practice this whole idea of changing a logarithmic equation to an exponential equation, or changing an exponential equation to a logarithmic equation. let's take a look at this first one. Let's see here. Log base 3 of 81 equals 4. So rewriting that as an exponential equation, we would have 3 to the 4th power equals 81. And of course, this is true. 3 times 3 is 9, times 3 is 27, times 3 is 81. But again, notice the base is the same, but the players changed places in terms of who's connected with the 3. Any questions about that one? Okay, here's another one. Log base 10 of 100 equals 2. Writing that as an equivalent exponential equation, you would have 10 squared equals 100. Any questions there? All right, let's take a look at another example. Log base 6 of 1/36 equals -2. The exponential equation equivalency would be 6 to the -2 power equals 1/36. Let's see, how about this? Log base 8 of the cube root of 8 equals 1/3. If we wrote that as an exponential equation, that would be 8 to the 1/3 power equals the cube root of 8. And doesn't 8 to the 1/3 power equal the cube root of 8? That's just exponential versus radical notation. Okay, let's see, how about this one? X equals log base 9 of 81. So this becomes 9 to the x power equals 81. Any questions there? Okay, how about, let's see, log base m of p equals 101. So m to the 101 power, or the 101st power, equals p. In each case, the base is the same, the players or the numbers change places. Any questions before we go on? All right, now we're going to go the other direction. We're going to take exponential equations and change them into logarithmic equations. So let's say I've got 10 cubed equals 1,000. So this would be log base 10 of 1,000 equals 3. 3 to the -4th power equals 1/81. Log base 3 of 1/81 equals -4. M to the n power equals p. Log base m of p equals n. Any questions? So you're all experts at playing baseball? Okay. 12 to the -2.6 power equals n plus 1. So this would be log base 12 of n plus 1 equals -2.6. But in this case, all right, in the exponential equation form, because n plus 1 is all on one side of the equation, it's kind of grouped. But when we change it to logarithmic form, we need parentheses around it because it's the log base 12 of that whole quantity. If we just leave it like this, that would be log base 12 of n plus 1. And we want the log base 12 of the quantity n plus 1. So be careful with your grouping symbols. Okay. Now, we're going to solve some equations. And this is a rule that's not, I guess I shouldn't call it a rule, but it's not true 100% of the time, but darn close to 100% of the time. And that is when you're dealing with exponential equations and logarithmic equations, if you're asked to solve an exponential equation, quite often you end up converting it to a logarithmic equation in the process. Or if you're asked to solve a logarithmic equation, quite often you change it into an exponential equation in the process. All right, here we have log base x of 9 equals 2. Okay, so writing that as an exponential equation, we would have x squared equals 9. Any question how I got there? All right, now, if we go back to chapter, let's see, is it 10? Yeah, the square root property or the principle of square roots, we could take the square root of both sides and we get x equals plus or minus 3. However, there's a problem here. X cannot equal -3. And why is that? Well, let's do some exploring, some reviewing of what we looked at yesterday. We talked about if we have something in the form, let's say y equals b to the x power, an exponential equation, b has to be greater than 0 and b cannot equal 1. Okay? Do you remember that from yesterday? Hopefully. Well, if I take this this exponential equation and I convert it into a logarithmic equation, it becomes log base b of y equals x. Now, this b is the same as that b. So if this b has these restrictions, so does that b have those restrictions, which means that b can't equal 1 and b has to be positive. So now let's go back here. That's why x cannot be -3. Log base x, x has to be positive and not equal to 1. So even though solving this equation, we would get potentially 2 solutions, the negative solution does not work in terms of logs. Okay, any questions about that? All right, let's say we've got log base 7 of x equals 0. So changing that to an exponential equation, 7 to the 0 power equals x. Well, what does a base that's not 0, so 7, raised to the 0 power, what does that equal to? Do you remember that from yesterday or from previous quarters? Anybody? Well, it's equal to 1. You're the quiet type today, huh? Okay.
Can't it not equal 1 in this case?
Oh, okay. Because you're saying the base can't be 1?
Right.
Okay, the base isn't 1. The base is 7.
Oh, wait, no, but the base is, okay, never mind.
Yeah, basically what we've got is this. Yeah, we can take the log of 1, we just can't take log base 1, okay? All right. How about this? Log base 4 of 16 equals x. So this becomes 4 to the x power equals 16. All right, now, if we can rewrite this equation so that it has 4 to the x equals 4 to, I'm going to write some power, then the exponent on the left would equal the exponent on the right. This has to do with something called one-to-one functions. that we aren't covering in Math 93. It's in some of the sections we skipped. So I guess you'll just have to take my word for it that in this context, if we have 4 to the x equals 4 to some power, the exponents are equal. So where does that get us? Well, let's see here. Okay, having too much fun. Could I write 16 as 4 to some power? Is 16 equal to 4 to some power? Isn't it 4 squared? Therefore, x equals 2. So log base 4 of 16 equals 2, or 4 squared equals 16. Any questions there? Okay. Let's see here. Log base 3 of x equals -4. So to solve for x, I could rewrite this logarithmic equation as an exponential equation. 3 to the -4th power equals x. But isn't 3 to the -4th power the same thing as 1 over 3 to the 4th, which is the same thing as 1 over 81? So log base 3 of 1 over 81 equals -4, because 3 to the -4 power equals 1 over 81. But the answer to our question would be 1 over 81. Okay, let's see here. Log base x of 1,000th equals -3/2. So writing that in exponential form, we'd have x to the -3/2 equals 1 over 1,000. Okay. So recall that a power raised to a power, you multiply the exponents, right? So x cubed to the 4th power would be x to the 3 times 4, or x to the 12th power. What could I raise both sides to? What power? So that on the left, I would just get x. Well, we're going to multiply this exponent times whatever exponent we put here. -3/2 times what is 1? Wouldn't that be -2/3? So -2/3, -2/3. Do you see how I got that? Any questions there? So now the question is, what is that? Well, 1 over 1,000 to a negative power would be equal to 1,000 over 1 to a positive power. Well, x to the 1 is just x, and 1,000 over 1 is just 1,000. So 1,000 to the 2/3 power. Okay. Now, recall I could take 1,000 to the 1/3 power and then square it. But that's the cube root of 1,000, which is 10. And 10 squared is 100. So that kind of took us back to chapter 5 and chapter 9, I think it is. Yeah. So basically, log base 100 of 1,000th equals -3/2. But x is 100. Any questions about that problem? That one got kind of complicated, I know. Okay. This next set of instructions says, evaluate each logarithmic expression. And this is without a calculator. Okay, log base 3 of 9. Well, what I'm going to do is I'm going to say, I don't know what that equals, so I'm going to say that it equals box. Okay, some answer. Log base 3 of 9 equals box. But now I could change this into an exponential equation and say 3 to the box power equals 9. But if I could write this so that I had powers of 3 on both sides, the exponents would be equal. Well, 9 is 3 to the second power, therefore the box equals 2. So log base 3 of 9 equals 2. Any questions there? Okay. Now, this says log of 100,000. No, that's all it says. Well, there's something missing here. What's missing? What didn't I write that maybe I should have? Anybody?
What it's equal to, right?
Well, we're going to say it's equal to something, but back here, there's something missing.
The sub number, right?
The base, right, the base. Okay, so here's the dealio, all right? Log base 10 is used quite a bit in mathematics. And I don't know if you've noticed, but mathematicians are lazy. I mean, they're efficient in that if something is used over and over and over, they tend to shortcut it. For instance, let's go back to chapter 9, I think it is. If we're going to take the cube root of 8, we put an index of a 3. But if we're going to take the square root of 4, we don't bother to write the 2. We just understand that if there's no index written, it's an implied 2 for square roots. Well, mathematicians decided that because log base 10 is so commonly used, they're not going to bother to write the base. So just log, which is referred to as common log, this means log base 10. And in fact, I don't know if you have your scientific calculator handy, but if you do, look over on the left column, and somewhere probably in about the middle of the column, there's a button that says log. Also, if you look at the second function key of that button, it is 10 to the x power, which is also a clue as to reminding you that log is the same thing as log base 10. Okay, so this is a notation that you need to get used to. So log is the same thing as log base 10. So back to the problem. It said log of 100,000. Okay, so I'm going to go ahead and remind myself that there's an implied 10 there. And I'm going to say, I don't know what it's equal to. We'll just call it box. Okay. So then 10 to the box power equals 100,000. Whoops. 100,000. There we go. So if I were to write 100,000 as a power of 10, what would the exponent be? You just count the zeros, don't you? Remember that? So what is a box? It's equal to 5. So log base 10 of 100,000 equals 5, because 10 to the 5th power equals 100,000. Okay? Are you still trying to figure out where the 5 came from? 10 equals 10 to the 1. 100 equals 10 to the 2. 1,000 equals 10 to the 3. 10,000 equals 10 to the 4th power. 100,000 equals 10 to the 5th power. Look, I'm just counting the zeros, aren't I? I mean, that works in that context. Okay. All right, now we're actually going to use our scientific calculator. So hopefully you have one handy. And if you don't, you can go back and do this later when you do. It says, use a calculator to find each value. Give answers to 4 decimal places. All right, we have the log of 0.57. So that's log base 10. But again, on my calculator, there's a button that says log. So when I push that button, I get that. I get a left-hand parentheses. Then I'm going to put in the 0.57. I'm going to put a right-hand parentheses there, equals, and I get negative 0.24412514443, and then it runs out of room. But it said to write it to 4 decimal places. So that would be right there. The 2 would round down. So I'm going to get negative 0.2441 would be my approximate answer to 4 decimal places. All right. Any questions on that? Here's another one.
What happens?
Yes.
I have a quick question. What happens if you're using the calculator and it's not log 10?
We'll get there. There's something called the change of base formula. I can't remember who it was, but somebody emailed me yesterday and they said, is it true that section, let's see, is it section 6 and section 7 and the chapter review are all due on the same day? They didn't say this, but I'm sure they were thinking, oh, that's so overwhelming. In section 11.6, I think you only have 4 or 5 questions, and they have to do with something called the change of base formula. So we're going to learn to use base 10 and base E. We'll talk about that tomorrow. But then when we have something like log base 2, how do we deal with that? And this change of base formula that we'll be learning helps us convert any acceptable base into base 10 or base E. So coming attractions, okay? We'll get there. But that's a good question.
Okay, thank you.
You're welcome. Okay. So let's say I've got log of 375.876. All right. So again, that's log base 10. So log parentheses, and then I put in the 375.876, close it up, and I'm getting 2.5750. The 4 would round down, so 2.5750 is what I would get. Okay, and again here, I'm going to put that number in there and then close it up. Any questions on that? Okay, now it says use a calculator to solve each equation. Round answers to 4 decimal places. This says log of x equals 2.8945. So what's implied that's not written in this equation? The fact that it's log base 10, right? And I know it seems kind of annoying. It's like, wow, can't they just put it there? Does it really save that much time? It's so much easier if I don't have to remember that. This is true of basically in any discipline. There are shortcuts within any subject where if something's used over and over again, they shortcut it, but it makes it harder for those of us on the outside trying to get in and learn all the stuff. So rewriting this as an exponential equation, it would be 10 to the 2.8945 power equals x. On my calculator, there's a couple of different ways I can put this in. I can just use a plain old 10. Then I can use the little power key that looks like that. And then I can put in 2.8945. So 2.8945, and then push enter equals, and I get 784.3321189, which would be 784.3321, because going out 4 places, we'd get that. Okay, so I can do it that way. Another way I could enter this into my calculator, remember I said that the second function key of log was 10 to the x? So I could start out with a second function log, which gives me this second function log. And what actually shows up looks like this: 10 with a little caret parentheses. Then I could put in my 2.8945 and close it up. Let's see. Oops. 2.8945, close it up. And I get the same answer I got that way. So, you know, it's just a matter of how you want to do it. Okay. Any questions there? Let's take a look at this problem. Okay, it says stocking, not as in stockings, but as stocking, putting fish, stocking lakes. A farmer stocked a lake on her property with 75 sunfish. All right. Now, she was told that with the proper oversight, the sunfish population could be approximated by the logarithmic function f of t equals 75 plus 45 times the log of t plus 1, where t is the number of years since the lake was stocked. Find the number of sunfish you can expect in the lake in 2.5 years. So t equals 2.5 years. Okay. Now, notice log, log, so that's log base 10. Okay. T is 2.5. Let's use 2.5 just to make it easier to work with. So f of 2.5 equals 75 plus 45 times log of 2.5 plus 1. Now, I can simplify 2.5 plus 1 and write it as 3.5, or I can just group it with parentheses when I punch it into my calculator if I don't want to bother to simplify it further. I'm not going to bother. So I'm going to go 75 plus 45. Let's see here. Hang on, I pushed the wrong button. 75 plus 45 log, parentheses, 2.5 plus 1, close parentheses, and I come up with 99.483. Now, let's see. If you had 0.48 of a fish, that probably wouldn't be really good for the poor fish. So it seems to me that we would have approximately 99 sunfish. A little bit longer, we'd have 100, but okay. Questions on that? Let's see. We've got one more example here I'm going to do. This says children's height, so how tall a child is. The logarithmic function h of a equals 29 plus 48.8 log of a plus 1 gives the percent of the adult height a male child a years old has attained. If a boy is 9 years old, what percent of his adult height will he have reached? So we want to find h of 9. So we're going to get 29 plus 48.8 log of 9 plus 1. Here again, I can keep 9 plus 1, put it in parentheses, or I can simplify it and turn it into 10. It's still going to be in parentheses because when you punch in the log button, most calculators put a right-hand parentheses anyway. So let's see, 29 plus 48.8 log of 9 plus 1, close it up, and I get 77.8. Now, it said what percent? So this is a percentage. So that means by age 9, an average male child has reached 77.8% of their adult height. Any questions about that? All righty. So don't forget, log means log base 10. Changing from exponential to logarithmic form, or the other way, the base stays the same. The two numbers change places. And with that, I shall bid you adieu. I shall be back this afternoon at 1:15 if you have any questions. With that, we'll stop the recording.